Hello, everyone. Thank you for this opportunity, Professor Evans, to talk to our prospective students for 10 minutes. My name is Nathir Rawashdeh. I'm an assistant professor in the Department of Applied Computing. I teach courses in electrical engineering technology and in the mechatronics study program. Um, yes, this is my email address if in case anybody wants to contact me, and here's my lab website. Today, I want to talk about three things, slightly related. The focus is on computing, and why is that important in relation to mobile robots and autonomous cars. So, the first thing I want to talk about is how to use artificial intelligence to detect the drivable path on a road that is covered with snow. I mean, humans can barely do that. If the snow is covering the road, it's difficult to find the road, right? But I'm going to show that artificial intelligence can do that and can help a human driver. I also want to show a mobile robot, this picture here, with a ultraviolet light on it. This can disinfect rooms like hospital rooms or libraries or grocery stores. Of course, the UV light is harmful to humans, not all wavelengths. So this robot has a harmful wavelength and a not so harmful one. Um, and I'll talk about this more. And I want to show you my website and what kind of work students are doing with me and what work we have done in the past. So I want to talk about autonomous driving. Today cars have a lot of sensors on them. So let's take a look at this car here. The green is a radar. There's a long range radar, like here, short and medium range radar, like these lobes here, the green ones. So with long range radar, a car could, for example, detect the car in front of it and keep a distance. This is called adaptive cruise control. You could use radar to detect cross traffic, like if a deer crosses in front of the car, suddenly the radar can see that even at night or if it's snowing or raining. And then maybe the car can stop automatically. Also, blind spot detection. If you're driving a car and want to change lanes, you always have to look to make sure there's no car behind you that you might hit when you change lanes. So this is in the mirror, there's a spot a car can hide and you can't see it in the mirror, but it's right next to you. This is called the blind spot. So you could use a radar to detect cars there. There's also cameras, the gray lobes. Like you can have cameras on the sides and looking backwards, like the parking camera that every car has today. You could have the camera point forward to detect traffic signs, for example, a stop sign maybe, or a traffic light. And you can also detect lane markings on the road to keep the car inside the lane. So the markings on the road, only a camera can do that, right? You can't really sense that any other way. There's also LiDAR, which is a laser based sensor. It's like a laser beam that goes back and forth. The laser bounces off objects, and the sensor then knows how far away the objects are and where they are, in front of me or to the right of me. Yes, and the problem with lasers is that when it's raining, the laser beam scatters and doesn't return to the sensor. So the laser sensor cannot work in the snow. If it's snowing or if it's raining or if it's hazy. Cameras also have a problem when it's hazy. Or so radar works there, but radar has low resolution. You can't really get a very detailed picture using radar with today's radars. There's work going on in radars to make them better. But anyway, so that's where we're at. And the last sensor here, the purple one, is ultrasonic sensors. Those are very short range, so they don't really work if you want to drive on a highway. They can't really help you. But for parking, they're useful. Like when you back up your car, it starts beeping when you're about to run over the bicycle, for example. You know. So this is what happens today. So there's all kinds of sensors. And then I also want to say something about the computers on board of a car. You can see this relates to computing. I mean, all this data has to be processed. So in today's cars, we have a distributed architecture. We have one engine control unit or processor for every task. Okay. In the next 5 years, there will be more domain-specific CPUs, engine control units. For example, you could have a controller for entertainment, a controller for climate control, a controller for the powertrain, how the wheels are moving, maybe a controller to get all the sensor data, and another one for safety, automatic braking, for example. In the next 10 years to 15 years, there will probably be a supercomputer inside of a car that does all the work instead of having many computers. So maybe 15 years from now, the car will just be almost like a cell phone on wheels, that can do all kinds of processing. It won't just be a transportation device anymore. And in this future, 15 years from now, people are expecting more than 300 million lines of code. And this is all computing, and there'll probably be a lot of artificial intelligence in there. So we did some work on data. There is research on autonomous driving, but most of it is trying to perfect driving and in a perfect environment, like here, nice and sunny, um, roads that have markings on them, and everything's cool. And you can see the sensor package on the top of the car. Also in the front, there's a weird radar thing here and here as well. There could be a camera here as well. So, but this is what car companies today are doing, like Tesla, GM, Mercedes, Audi, all of them, and the Amazon cars and the Google cars, they're all trying to get it working in perfect weather. This is a very difficult problem because there's an infinite amount of scenarios that could happen to the car. I mean, how would you teach a computer to be truly intelligent, to be able to react to something it has never seen before, like a human does? So there is this data set we took that recorded data in the snow. Like here, you can have snow tracks, you can have fog, snow banks. I mean, how would a car travel there? And this data set is called a dense data set. It is recorded in Germany, Sweden, and Finland in the winter. It has camera data, LiDAR data, radar, GPS, all kinds of data. They recorded about 6,000 miles of driving. And they labeled 12,000 pictures or frames for object detection in the snow. So we took that data set, which has been recently published. It's only February 2019. It's only less than a year old. It's more than less than 2 years old. And we took these pictures and we labeled them like this. This work has been done by my PhD student Nathir Rawashdeh. He took 1,000 of these pictures and he labeled them by hand like this in order to teach the neural net, the artificial intelligence. The idea is if you get this code that is intelligent and you give it examples of how the road looks in the snow, keep telling it. For example, you might tell it 800 times, 800 pictures like this, similar to this, with the labeled area. It will eventually learn, you know, and be able to predict the path, the drivable path, in a picture it has never seen before. So in these 1000 pictures, we take 800 for training and 200 for testing. And the neural net looks kind of like this. We take the camera image is processed, and also the LiDAR image, the laser image is processed, and the radar image. They're processed, and they all enter a neural net, which models how the human brain works. And this neural net, if you keep giving it examples, it will eventually learn. And then it can predict the drivable path, like this video here. So this is preliminary work, but it performs pretty well. So you can see all these frames, the artificial intelligence has never seen before, but it is able to detect the road. You know, it doesn't matter if it has tracks or not. And now the car is coming, and the underneath the car was not green, meaning it's not safe. And on the left here, you can see the actual picture. I mean, even for a human, it's hard to find the road. I mean, you look at this picture, you'll be driving really slow and looking for tracks and being careful, but the computer is able to do it. And this is the laser image, and this is the radar data. So this is pretty encouraging. We can do more by fusing the information better, performing sensor fusion, but this is pretty good. Okay. One last thing I want to show on it is a robot that disinfects spaces. So I'm going to run the video and talk about it. So this has been sponsored by a Paul Williams Seed Grant. That's why I called the robot Paul 222. It can disinfect public spaces. It kills the coronavirus by damaging its DNA, so it cannot reproduce. So if there's a virus on the surface, it'll just get damaged by the radiation and cannot reproduce. So here we have two types of light. This light we're seeing now is the dangerous wavelength that causes cancer. And this is the new light, which is a 222 nanometer light, which does not cause cancer. And here we measured how long it takes to disinfect. And these are our labs, and we have first-person view in the robot, so we can drive it around the corner. This is just driving by the husky statue in the snow. Okay, the last thing I want to show is my website, morolab.mtu.edu, Mobile Robotics Lab. If you go there, you'll see, I hope this is shared. You'll see basically three pictures. One of them is people, publications, and capabilities. So let's look at the people. These are all people who have been working with me. I've only been at the university for 3 semesters. So some people did some work on autonomous robots and AI. These students did some mobile robot simulations. I don't know if you can see those. They used some open source software to simulate robots because they were not able to do the actual programming because of COVID lab closures. And this student here helped me with the ultraviolet robot. These are senior design students who are working on a robotic arm with a camera attached, and some other students are developing automatic control, a system for automatic control. And this is the PhD student. If you look at my publications, I tried to get all the mobile robot stuff in one place. Some of these publications have videos. This is a mailbox robot that knocks on the door. This is a robotic cart that follows you around. This is a competition we participated in many years ago. Yeah, and yeah, that's what I wanted to show. And finally, these are the lab's capabilities. We have sensors to measure UV light. We can build mobile robots. We have laser, depth cameras, and radars. We can simulate. We can do thermal imaging and image analysis. We can build custom electronic circuits, and we can implement artificial intelligence. Yes, so with that, I wanted to end this meeting, and I wish you the best of luck, and I hope you find the major you like. Thank you very much.